Hello, this is video recording for session 10 of the PMRF session, nptel session. So question 1 is an attack on a crypto system where the attacker attempts to use all possible permutations of keys is called. The options are brute force attack or birthday attack or known plain text attack or chosen plain text attack. So the answer to this question is, so when the attacker uses all possible permutations of keys, that's the most simple strategy for any attack, and that's called brute force. That's also called exhaustive search. That's another name for this attack, where the adversary goes over all possible keys and then checks which of these keys satisfies the given constraints. Right. So that's the simplest form of attack. That's called brute force. So what is just to describe what is birthday attack? So for that, we first need to look at this mathematical concept called the birthday paradox. So what is the birthday paradox? States that if there are 23 children in a class, then the probability that any two of them share the same birthday is around 50%. So why is it called a paradox? This is a paradox because in any group of people, we don't expect too many people, or we don't expect to find even two people who have the same birthday. But the paradox is that even in a small group as small as 23, even in such a group of small size, the probability that such a that there will be two people with the same birthday is high, pretty high. It's at least half, right? So that's why this is called a paradox. And in fact, we can do this computation. So let's say that there are n children in the class. We want to compute the probability that all of them have different birthdays, and we can subtract this from 1 to get the probability that there are at least two who have the same birthday. So what's the probability that all of them have different birthdays? So this would be total number of favorable outcomes divided by the total number of outcomes. The total number of outcomes means assigning birthdays to n different people, right? So if we were to assign birthdays to n different people independently, then for each person there are 365 options for birthdays, assuming no leap years or anything. So there are 365 options, so there are overall 365 to the power n, because each person has 365 options, and we can multiply these number of options to get the total number of assignments. So there are 365 to the power n total assignments, and two of birthdays to these n children. And the favorable assignments would be those where each of them have different birthdays. So to find the total number of favorable assignments, we can proceed sequentially. So let's say for the first child, we assign the first child a birthday. So there are 365 options for the first child. Now, once we have assigned a birthday to the first child, for the second child, since we want different birthdays to be assigned, we don't want the same birthday that was assigned to the first child to be assigned to the second child, right? So for the second child, now we have one less option for assigning a birthday. So for the second child, now there are 364 options. Similarly, for the third child, there will be 363 options, and for the nth child, there would be 365 minus n minus 1 options for birthdays, because n minus 1 children have been assigned birthdays, right? So this is the total number of favorable outcomes. And if we compute this probability, if we simplify this calculation, we can write it as 365 factorial divided by 365 minus n factorial times 365 to the power n, right? So if we do some calculations, if n is 23, this value is very close to zero point 0.5. This is 0.49. So the probability that there are two children who have the same birthday would be around 0.51 in that situation. And when n is 30, this value is almost zero point 0.3, which would mean that the probability that there are two children with the same birthday would be zero point 0.7, right? So this is called birthday paradox. Now, How is that relevant for security purposes? So if you remember, for any hash function, we need this property called collision resistance, right? So uh, we don't want there to be two different images, pre-images which map to the same image under the hash function. The thing is that there will be such pre-images because the hash function is a compressing function. So the size of the range is less than the size of the domain. So there would be more than one pre-images which map to the same output. But we don't want any adversary to be able to find such collisions efficiently. So this property is called collision resistance. And the birthday paradox basically states that if you consider a good number of samples, you don't have to consider a lot of samples. Like even if you, let's say you assigned, so the hash output was assigned randomly to different values, then once we have 23 or so values, right, small number of values will have collisions. So there is a high probability that we would encounter collisions if we sample enough number of times. And we don't have to sample a lot of times. That's what the birthday paradox states. So the birthday attack is relevant for hash functions. It basically says that if we have a good number of hash samples, we don't need too many hash samples. That's according to the birthday paradox. Even then, there is a high chance of collision, right? So that's the birthday attack. Yeah, so one could find collisions quickly and break hash function security. Okay, so let's move on to question two. Question two says a signature scheme is said to be computationally secure if option A, it is infeasible to verify message signature pair for an adversary. Option B, the adversary cannot produce a valid message signature pair given only the verification key. Option C, the cost and time required to break the cipher is unbearable. And option D, all of the above. So the answer for this is option B. So let's go over the options one by one. Option A is definitely not true because in a signature scheme, by default, any party in the system should be able to verify message signature pairs efficiently. So even the adversary, you just need the verification key, and the verification key is supposed to be public. So even the adversary can verify message signature pairs efficiently. So that's not true. Option B, the adversary cannot produce a valid message signature pair given only the verification key. That's true. That's called unforeseeability requirement, right? It's very similar to the real world scenarios where we don't want any malicious party to copy our signature. So that's why we sign. That's why we are required to sign on many places because the hope is that no malicious party would be able to copy our signatures, even though that's not entirely true in the real world. But in the digital world, it's mathematically proven that these message signature pairs cannot be produced given just the verification key. So that's option B is true. Option C, the cost and time required to break the cipher. So there is no cipher in signature schemes. That's encryption scheme. So yes, only option B is true. Okay, so let's move on to question three. Question three says that network security ensures to option A, detect an attack. Option B, prevent an attack. Option C, recover an attack. Option D, all of the above. So yeah, so this the answer for this should be all the three options, right? So in the course we didn't go into detail as to how these three things are implemented, but they can be implemented using different techniques. So for example, for detecting an attack, signature schemes could be used. So that's one example of detection of an attack. So when we use a signature scheme and send the message across a public channel, there is no way that the adversary could have modified a message and still the signature was a valid signature, right? Because that would break unforeseeability. So signature schemes by default are used to ensure this property called integrity, and that is attack detection at its core, right? So there was a question in the session about modes of operation. So one important thing to note with modes of operation is that they can be applied to any block cipher, not just to DES. So DES is one example of a block cipher. But if we are given an arbitrary block cipher, even with that we can apply these modes of operation, right? So with any block cipher, a mode of operation can be applied, right? So just to describe it slightly in slightly more detail. So what is a block cipher? So for a block cipher, we divide the input plain text into blocks, and the cipher only works on fixed lengths, right? That's why each block has to be of that fixed length. It can't be more than that, because then the block cipher wouldn't work on that length, right? So we have to divide plain text, which can be a very long string, into blocks where each block has to be of that fixed length on which we can apply the block cipher and get a ciphertext. But how do we combine these ciphertexts, right? We get, so apply different ciphers to different blocks, we get different ciphertexts, but how do we combine these? So the way to do that is what's called modes of operation, right? So for example, one mode of operation is this counter mode, right? So what do we do in this counter mode? We have a counter, and for each block we keep incrementing the counter. So for the first block the counter value is 0, for the second it's 1, and so on, right? Now how do we apply the mode of operation? So we pass this counter value through the cipher, which could be DES or AES or any arbitrary thing. We have a key, we use this key for the cipher, we pass the counter value as the plain text to the cipher, we get a ciphertext. And we had an original plain text block, right? We divided the plain text into blocks, and the first block we then XOR with this the output of the cipher on the counter, and we get the first ciphertext block, and we repeat this process. So we can parallelize this process also, right? We can do it for different counters. There's no link going from first operation to the second operation and so on. So we could even parallelize these operations for counter mode. So similarly, for the second block, we'll have the counter value to be 1. We'll pass it through the cipher. We'll using the same key, and we'll get an output, and we'll XOR this with the second block of the plain text to get the second block of the ciphertext and so on. Right. So there was a question like, what's the counter value? So the maximum counter value would be the total length of the plain text divided by the block length, right? Or it could also be the total number of rounds that have happened so far divided by the number of rounds in each cycle. These are just numerical facts. It's not too hard to see. Okay, so for the next question, which of the following is a generic attack on block ciphers? Option A, linear cryptanalysis. Option B, exhaustive search attack. Option C, differential cryptanalysis. And option D, boomerang attack. Right? So first of all, what does it mean by a generic attack? Right? So generic attack means that there is no condition. We don't need any other condition on to perform this attack. Right? The most basic possible attack that you could think of. That is what is called a generic attack, right? So we don't have any conditions. We are not specifying whether it's a chosen plain text attack or a known plain text attack. Like no other condition on the kind of attack. What's given to the adversary, no condition. Just a simple plain text ciphertext pair, no matter how it was chosen or whether it was known or any condition, any other condition, it's not given, and even then we should be able to perform the attack. So brute force or exhaustive search is obviously one of such attacks, right? So brute force you can do. So even if you have any plain text ciphertext pair, no matter how you got that pair, you can always do brute force. So that's a generic attack, right? Differential cryptanalysis is definitely not a generic attack, because we need to be able the adversary needs to be able to choose plain text and get the corresponding ciphertext, and then modify that plain text in a predictable pattern, and then see how the pattern shows up in the ciphertext, right? That's what's called differential cryptanalysis. And that, so we need the adversary needs the power to choose plain text at least, to perform differential cryptanalysis. So that's not a generic attack. And boomerang attack is a even more uh, advanced version of differential cryptanalysis. With linear cryptanalysis also there is some pre-processing to be done. One needs to form these equations relating the cipher and the plain text and the ciphertext and the keys, right? So it's not exactly a generic attack. There are some more conditions to be specified. In particular, we need to analyze the cipher more carefully when doing linear cryptanalysis. So exhaustive search is the most simple, the most basic generic attack that is possible on any block cipher. Okay, so for the last question, Hellman table is a part of A option A boomerang attack, option B linear attack, option C time memory trade-off attack, or option D man in the middle attack. So this is again a factual question, and the answer is time memory trade-off attack, TMTO attack. So there's no as such explanation for this. It's just a factual question. So just to describe what's a man in the middle attack. So one way to do this man in the middle, one way where it's used by adversaries is in triple DAs, but that's not what I'm discussing here. There is this another version where we have party A and party B, right? And ideally they should be interacting with each other, but there is all in reality there is an adversary in the middle, and the adversary is actually interacting with both party A and party B in a way that the adversary interacts with party A playing the role of party B, and it interacts with party B playing the role of party A, right? This general situation is called a man in the middle attack, and it can be used to break security in many places in many situations. Okay, so there was one more question, like how do we solve this? So for example, if we have to compute this a to the x mod n, right? How do we do this efficiently? So if a is co-prime to n, then we can use Euler's tuition theorem to say a to the x mod n is same as a to the in the exponent x mod phi n overall mod n, right? So this reduces the exponent. So this is one thing we could do, right? But in some situations, for example, when n is very large and x is also large enough, then doing this might not be helpful. So in those situations, we need to compute use this repeated squaring method, or this is also called square and multiply. So repeated squaring is only for 2 to the power something that is also a power of 2. So if you have 2 to the power something in the exponent which is also a power of 2, you can use repeated squaring. But for general situations, you can break the exponent as sum of powers of 2, and then use repeated squaring for each power of 2, and then multiply all these together. So that's why this is called square and multiply, right? So that's the most basic strategy when you want to compute a, an element in this in general a to the x model. So that's the best possible strategy in many situations. For example, if you had to compute this 2 to the 67 modulo some large prime, how would you do that, right? So so the way you would do that, for example, if the prime was 1107, so how would you compute 2 to the 67 mod 107, right? So one way to do that would be to write 67 as powers of 2, sums of powers of 2. So 67 would become 2 to the power 6 plus 2 to the power 1 plus 2 to the power 0. And once we have done that, we can use square to first compute what's 2 to the 2 to the 6, what's 2 to the 2 to the 1, what's 2 to the 2 to the 0. 2 to the 2 to the 0 is just 2, right? 2 to the 2 to the 1 is 2 to the 2 to the 0 whole square. 2 to the 2 to the 2 is 2 to the 2 to the 1 whole square, and so on, right? So if you do this 6 times, you'll have 2 to the 2 to the 6, and then you can multiply all these three values to get 2 to the power 67. Right, one final point to mention for quadratic residues. So if you have a prime p modulo p, if you want to find whether an element A is a quadratic residue or not, there is a very quick way to do that, which has been mentioned in previous lectures also. So if A is a quadratic residue modulo p, then A to the p minus 1 over 2 has to be 1 modulo p. And this condition is only true for quadratic residues. Right? For general elements, we have Fermat's little theorem, which says that A to the p minus 1 is equivalent to 1 modulo p for all A. But for quadratic residues, for all in zp star, for all A which are co-prime to p, Fermat's little theorem holds. But for quadratic residues, there is an even a different condition that also holds, which is A to the p minus 1 over 2 is also 1 modulo p, because A is b square for some b which is co-prime to p. So b to the p minus 1 is 1, so that's why A to the p minus 1 over 2 is b to the p minus 1, and that's also 1. Right, so this condition holds for quadratic residues, and it can also be shown that this only holds for quadratic residues. Okay, so if you have if you want to check if a given element is a quadratic residue modulo p, there is an easy way to do that. Okay, so that brings us to the end of our session. Thank you.